Right, okay, so having given the introduction about the energetics of industrial processes, now what I would like to discuss with you is how do we analyze the energy consumption of a process? And for you, most of it has no big meaning. So if I tell you what would you do if you have a process and you have to analyze the energy consumption? So let's assume that you are a new engineer, okay, hired by in a company, and then the boss says, okay, let's analyze the energy consumption of the process. So what would you do? Yeah?
I would ask for the bills, the electricity bill, natural gas bill, in order to see like the first approach of how much they are consuming.
Okay, so the answer is correct, because this is the first thing we do. We look at the bill. The bills, because this is a tangible, the visibility of the process is this. We see how much electricity, how much natural gas we buy. But if I'm telling you that I would like you to analyze the energy consumption, so what would be your next step then? Let's assume that you have the bills.
I would analyze the states, for example, the beginning state and the end state.
Of what?
Process. For example, if I'm using a fluid in the process, fluid state.
Okay, so you will look at the different states of what? Of fluids, of flows in the process? Okay, and what would be the purpose of doing this?
Measuring the energy difference.
Okay, and what do you have in mind by doing this?
Because if I measure the energy difference, I might have an idea about the consumption of the energy.
Okay, so it means that what you would do is to look at the process units and try to see what is the energy difference that you will measure with enthalpy a priori, between the conditions at the inlet and the conditions at the outlet for the different process units. Okay, and how would you make the link with the bill then?
The price for the unit of energy.
Yeah, so that's correct. There is an idea there, because what you say is that the bill is not enough. I need also the price of energy. Why? Because if I have the bill and the price of energy, I know the energy. So it's not only the bill, it's now the energy flow. On the other hand, I don't see the link between the bill and the demand of a process unit. Can someone help him? So he's in his office and he's looking. There is a folder with bills, okay, and he takes this one, and then he's looking on the other side, and he finds process units, and then normally on the computer you have flows in the process units and temperatures that allows you to measure the energy needs. So what is missing there? Yeah?
I don't know if we said, but it's the price of energy. So each process unit is consuming a given amount of energy. If we know the price of that energy, that will come up to the bill.
Yeah, but I do agree with the price of energy, something that is needed. So I'm taking the bills and I transform it into money and energy. That's via the price, okay? But nevertheless, so there is something which is missing in the analysis, yeah?
I think that is missing could be efficiency. For example, a pump the pump uses more energy than the energy of the states.
Yeah. You are a mechanical engineer.
Yes.
Okay. So are there some chemical engineers in the room? Yeah, Rafael, I know. No other? So you are all mechanical engineers? Okay. Yeah, but it's interesting because you are answering like a mechanical engineer. And I see why. But still, what is missing? So I'm asking you to analyze the process, the energy consumption of a process. Yeah?
If we are thinking of chemical reactions, we have to take into account the energy that will be produced for the reaction. We have to retrieve that from the
Yes, this is correct, but you are still working with units. Okay? I'm asking you to analyze the process. So what is missing?
The time.
Huh?
The time.
Yes, the time is there as well. So I do agree. So in fact, the energy bill is the integral over time of the energy consumption. But I want you to analyze the process energy consumption.
So you also need the model of the process somehow.
Yeah, I would say it would be nice to have, okay, to have the model of the process. But what would be the purpose of modeling the process?
To identify the different consumers
Yeah, and
control it.
the controller. So you still, so but it's interesting. So I think that I have the. So what is missing? So first you have to define the system boundaries, okay, and then something which is important is the flows of raw materials and products. Okay, the reason for, if I'm asking you, give me the analysis of how you consume the energy in the process, you have first to ask yourself, so why do I need energy? And you need energy to make products. And I do agree that I will need all the flows afterwards, and a very nice model, of course. But I first have to look at what I'm going to produce, because this is what is going to produce to make my revenue. And what I have to understand is how the energy and all the support materials will be consumed in such a way that I will make the products that I want. Okay? So first step is look at the products, because I would like to, this is what is making my profit, right? And then afterwards you will then analyze the conversion of raw materials into products, and this will define an efficiency, and I can even do it without describing the process. Okay? Because now I can take the bill and I can make it per unit of product. And if I make it per unit of product, I have an indicator which is much more interesting than just knowing my energy bill, right? And then what I'm going to do is to write the energy, the mass balance here, which is going to define the flow that is not ending into products, which is finally the waste that I'm going to produce. The waste can be the emissions that I do in the environment, it can be the liquids that I'm going to release, it can be the solids that I'm going to release, and even the heat losses. So the amount of heat that I'm wasting in the environment, okay? And sometimes I'm wasting because I leave a door open, huh? Or I have to leave a door open. Okay? And then, of course, I will enter into the elements that are in the system. Okay? And we will end up by looking at the efficiency of the pump. And I will add something there. Because there is a risk of having... So what is interesting, that's why I was asking, are there people from chemical engineering here? Because most probably the people from chemical engineering will not care about the efficiency of the pump. Okay? They will say, I need a pump and I put the pump there. Okay, because I need the flow to do, and I'm sure that I will have a good pump, right? But at the end, a chemical engineer would say, okay, I'm going first to look at the products that I'm making. I'm going to write the mass and energy balance. And then, of course, I will go into more details of what is happening inside the system. So, and the way we do it is by having a list of steps. And the first steps is we have to identify from the energy bill what are the resources, the energy resources that we are going to consume. Okay? If I'm doing an analysis of the energy consumption, then I would like to know two things. First, I would like to know if I'm good in using the energy today, on a day-to-day or second-to-second basis. So the time dimension is important, okay? And I know that if my boss is asking me to analyze the energy consumption, he will also ask me try to reduce the bill. Okay? And the risk is to reduce the bill. Because the first thing you do, we have said the bill is two things, energy and cost. So the first thing that most of the people do is negotiate the cost. Okay? And now, if we have to reduce the energy consumption, then something which is going to happen is that either you will operate in a better the process that you are in charge, or you will do investment. And as soon as you will do investment, then you will have also to reduce all the variations coming from the time. Okay? You will try to identify what we name a baseline. It means the typical states under which the process has to operate. So I need to remove all the variations that are due to perturbations from outside, and because I need to make an investment that is made for the most probable operation or the best operation, expected operation of the process. So it means that I'm going to define a baseline, okay? Especially on the basis of the production. The next step that I'm going to do is to identify who are the energy drivers. That means that I have to look at who is consuming energy and who are the most important one. That's why I was saying the pump is probably not the most important one. Okay? I will concentrate on the biggest influencing elements in the process. Okay? And I can do it by, if I'm smart in analyzing the process. Okay? Which allows me then to say, I have identified who are the major consumers in my process, and now I can look at those consumers and look at their efficiency. And I will look at their efficiency by looking at their individual performances, but also on their impact, the impact on the other elements in the system. So if I have a very good compressor, it can reach a pressure that allows me to operate in new conditions, that allows perhaps to optimize the reactor operation. Okay? So it means that it will allow me to define where we are and what are the potentials. Okay? And at this place, I'm going to ask myself, so I can compare the energy that I'm spending with the energy that I'm able to define as being the needs of each of the process unit operation. Okay? Which allows me then to define, as soon as I know how much I should consume and I can compare to the amount that I'm consuming, then I have something which is interesting from my perspective, is that I have an efficiency indicator. Okay? If I know how much I need to heat a tank and I realize that I'm spending twice the amount, I have to ask myself, so where is the rest of the energy? Which then afterwards will lead to say, okay, operate better and perhaps we will have less losses. Okay? And then when I will have understood the needs, then I will start to do the integration of the needs. So look if there are synergies that can be created inside the system, if there are investment to be made. And again, I will, as you are creative, you will have a lot of options that will come in your mind. and there will be good options and less profitable options. And which means that you will have then to generate a list of options with a list of priority that allows to tell your boss, okay, if you give me 10 million, I'm doing this. If you give me 20 million, I will be this, this, and this, and you will save so much. Okay, so it means that you will have to classify the options. So how do we do this in a systematic way? So typically what we start with was the energy bill, and we try to go down from the energy bill to the process. Okay, and this allows us to see where the energy is flowing. Looking at different types of energy, so sometimes there is a process unit that requires a lot of electricity and another one that requires a lot of heat. I'm going to then prioritize the one that are consuming electricity and the one that are consuming a lot of heat, okay? So that I'm able to identify who are the drivers. From there, I will define what is needed to characterize all those flows, huh? And then you say, okay, I need temperatures, I need flows, I need to know where I am compared to where I should be. And in this case, you would need models, okay? Going into more details, going really from the top down to the process. Typically, there are steps there that are trying to verify that you are not losing information and that the information that we know enough, okay, and that we are consistent, okay. And then from there, we will be able to go in the reverse direction, in which we are going to say, okay, now that I understand what are the energy needs, I can then redesign the process in such a way that it will reduce the overall energy needs by creating, for example, having synergies. And so we will go in the reverse direction now, saying, okay, what can we do? What is the profit of what we can do? And then go back to the new energy bill. So I'm going to redesign the energy bill after having modified the process and calculating, therefore, in the reverse direction. So we have, what we name top down. We start from the energy bill, we go to the process by finding the priorities, collecting only the data that are needed, and then afterwards going in the reverse directions and regenerating solutions that can then be expressed and compared with the present situation, which allow us to finally generate solutions. So there will be always this top down, and you will see that you will receive a process flow sheet, and we will ask you modify give us the future energy bill of this process, okay? Per unit of product. Okay? So something which is important there is that I hope that you do not see a lot here. And this is by purpose, because this is exactly the type of flow sheets that you will receive. Here I have packed it on one slide, but typically you receive very big sheets of paper with a lot of flow pipes, vessels, valves, pumps, etc. Okay, then you realize that half of the pumps are there just in case the other is broken. Okay, that some of the pipes are just there in case of a leakage to blow and to avoid an explosion. Okay, there are some pipes that are just there for doing the control. So you were talking about control. So it means that you will have to debug this process, transform it into a processor that is transforming the whole flows that you see. Okay. And for doing this, then you will always apply mass and energy balances. Okay. The advantage of writing mass and energy balances means that what is entering the system is always leaving the system. Okay, it's just the only case where this is not true is in nuclear power plants, where they transform a little bit of mass into energy, right? But in all the processes that you will be facing, the mass balance is conserved and the energy balance, the energy is conserved. Okay, and it's very important. Okay, because something that does not end up as something having a value will be a waste. Okay, so if you know the waste you produce, you will see the opportunities. Okay, so it's very important to put numbers on all the flows here first before going down. Okay, verify that you are mastering those flows, and typically the ones that are difficult to understand are the one here. I'm just using this. So the waste flows are typically not well understood. Okay, and this is, yeah.
I think the heat losses, the unit of the heat losses should be joule per second.
Yeah, it's kilojoule. Yeah, you're right. 1 point for you. You're right. Something which is also important is that as soon as you have this, then you can also write the economic balance. So you have the sales, so what you produce, what you sell, what you buy in raw materials, the energy bill. And there is another bill which is quite interesting because you pay for releasing the waste, right? Okay? And at the end, you will have to make the bill. You have to look at what is the revenue, and the revenue is what you export, so the products times the specific value of the product. And you were talking about time. I'm using here the integral on the time, right? And this is also by purpose. Okay, it's possible that the product will have another value at another time of the year. If you are producing chocolate, the value of chocolate is higher just before Easter. Okay, it's logical, but it's true. Okay, ice cream, it's summer, right? So it means that the product can have different values, and as well for electricity that you can export. I'm writing the export of electricity by purpose because we are going to discuss about exergy, and if we want to reduce the exergy losses in the system, as the system is reversible, reducing the exergy losses means that we will make more exergy out of the system, valuable exergy, and the best way of, or the best the highest exergy value of an energy flow is electricity. Okay, so it means that sometimes we will sell electricity, and electricity will have also a price that can vary or depend on the time. So there is not a big value of producing electricity in the middle of the summer where Germany is producing a lot of PV panel, electricity produced from PV panels. Okay? And at the same time, the Switzerland has dams that are completely full because of the snow that is melting, and therefore they want also to sell their electricity. Okay? While in the winter it could be completely different. And then afterwards you will have the operating cost that is coming from the value of the raw materials that you buy, the fuel that you will consume, and of course, depending on the type of raw materials, you will perhaps consume more or less fuel. The electricity that you will buy or here, and the waste that you will produce that will also then have that will also have value. And by writing this, I have already written the overall economic balance of the system with what I have to pay and what I will gain from with the process. Okay? And still I have not seen the process itself. So now I have to go inside the process. And I'm going to try to understand what is happening there. And what is happening there means mainly tracking where the energy is flowing and under which form this energy is consumed. And what I'm doing here is I'm going to write flows of how the energy is converted, perhaps how the energy is wasted, how the energy is distributed, for example, using steam or hot water network, how the electricity is used inside the system, if what I'm doing with waste, because I can sometimes convert waste into energy by burning it. Okay, and what I'm going to and how I'm going to evacuate the heat of the process. So something that I'm looking there is to try to understand in which pipes the energy that I have seen as an energy bill is flowing. Okay, is it in form of steam? Is it in form of hot water? Is it in form of compressed air? Is it in form of cooling water? Okay, the in and the out are therefore converted into flows in pipes. Okay, and if I'm doing this, then I will have a much better understanding of what is happening inside. Which allows me then to have the complete picture. Something which is important is to understand the energy conversion. So what does it mean, the energy conversion? In fact, it's like looking at the interface between the energy that we buy and the energy that we use inside the process. Okay? And I'm defining it. So it's really an interface because it can be via different ways, so different water or steam. It can also be via the waste collection and then perhaps the recycling inside. Okay, and typically what we will have to look at is a list of steps that is finally converting, for example, the natural gas that I'm buying into steam. That the steam is going to be distributed and condensed in order to heat a flow, which is the process flow. So it means that I have at the same time at the first step a conversion process. Here with a certain efficiency, then you have a distribution line, and then you have the final usage, which is finally heating the process itself. Now this can be done in different with different kinds of vectors. Okay, and what we will do is that we will look at the different vectors that we will have. So we will look at the electricity, the steam, the hot water, the cold water, the refrigerated water, the glycolic water, the compressed air that will be produced from the energy conversion and distributed to the process unit. And there, my goal is to not spend time on useless things. So what I'm going to do is that I'm going to look at the process, look at the different process unit operations that are needed to transform the raw materials into products here. And for each of those, I'm going to make the list of the connecting distributed energy, electricity, refrigeration, etc. And then what I'm going to do is that I'm going to make a prioritization by using the rule of Pareto. And the Pareto rules is telling us that you will collect, in 20% of the time, you will collect 80% of the information that you need. And you will spend the rest of the time, so the 80% of the remaining time, to collect the 20% that remains. Okay? And if we want to be effective, it's important to concentrate on the 80%. Okay, the most important one. And what we will do there is that we will identify in those process units who is mainly consuming steam, for example. And as soon as I'm identifying that this unit is consuming steam, I'm going to calculate how much cooling water is consumed by the same unit and how much electricity is consumed. Okay? And I will do the same until I have explained 80% of the steam consumption for the different pressure level. I will do the same for the water. But I have, by characterizing the steam, I have perhaps already explained part of it. So I will continue. And at the end, so what we have shown, it was a study we did with Nestle. We have shown that by prioritizing, so we were looking at applying exactly this rule, so 80-20 rule, really pragmatic. We have shown that by only defining 30% of the process units inside the system, so 30% of all the process units, we were able to explain 95% of the bill. Okay? So it means that 65% of the process unit were not important for the energy bill. Okay? They were needed for producing good chocolates, okay? But it was not necessary to characterize them, okay? Exactly what the remark on the pumps, okay? By doing this, I have identified the 5 or 10 pumps that are very important for the process. Okay, all the others, they are there, and I don't care. They are representing peanuts in the energy bill. But by doing this, I'm going to go much faster, because then you do not make the list of all the pumps and characterize all the pumps. You just target the ones that are important. Okay? Another dimension that is important is to identify what are the major operating conditions of the process. So what are the states under which the process will be used? So the high production rate, the small production rates, and typically you can get those information from the measurements. So you see variations, no? Like what you have here. So this is the production level of a unit. And what you can see is that instead of having 8,700 hours to be modeled, I can define the process as being a process that will be operated under, so here there were only 13 periods. So instead of looking at 8,000 different states, I'm just looking at 13 different, clearly different states. So this is used by using techniques of from the data mining that allows us to identify what is the most frequent conditions. Okay, and then when I have this, then what I will do is that I will try to see if there are correlations. So if, for example, I can correlate a level of production and a level of consumption, which then allows me to know if some of the units are operating in good shape. I can give you the story of in the food industry, where when the production was 0, the energy consumption was only half. Okay, so what was happening is that the company was producing compressed air, and all the compressed air that was not used by the process was just wasted. Okay, but then by doing this, they did realize that there was a very big base load that they cannot justify, and they quickly then decided to change their the way to produce the compressed air. Okay, and this is done by trying to identify those correlations inside the system, which allows them to have a baseline that allows to know where we are and what is the reference. So we know how much we produce in the different periods, and we know what is the reference energy consumption. And if I have the reference energy consumption, then I can, for the same periods, then propose modifications of operations or modifications of improvement of the efficiency, and I will be able then to quantify how much I will win. Okay? For example, it's not necessary to add a heat recovery heat exchanger for something that is used only when you start up the process. Okay? The investment will never pay back. Okay, so this is the next step, and of course now something that I will have to do is exactly what you have said. So I need to characterize the flows in the system now. Okay, so I will try to see what is happening, and for this I will try to do or to develop information about different dimensions. The first dimension is the mass flow. So I will try to characterize where the mass is going inside the process. And then I will associate to this, and this is exactly what we have done in the reasoning, okay? I will add a value to all those flows, okay? Internal flows have values that are quite difficult to assess, but the one that leave the system, at least, we have an explicit value, right? And then I will go to characterize the thermodynamic state. So characterizing the thermodynamic state means that I need to know what is the enthalpy content of the different flows in the system in order to characterize the energy value of each of those flows. Which means that I will need to have something which is, that I will name the constitutive equation, that is going to make the link between the enthalpy content and the sensors that I have, the temperature, the pressure, or the composition measurements, okay? which then allow me to know what is at any time, in any state, what is the enthalpy content. And by the way, I will take also I will profit from this to at the same time to measure the exergy of the system by adding another dimension to it, which is the calculation of the entropy together with the enthalpy. Okay? Now I need the value of the enthalpy, I need the value of the entropy as a function of the temperature, as a function of the pressure, and as a function of the composition. So it would make sense to have tools for doing this. Okay? And he was talking about models. Models exist. So there are professional tools that allow us to characterize flows and make the thermodynamic calculations. Okay, and there are even open source, although they are not really efficient, but there are open source software that allows you to calculate either the flow sheets or at least the thermodynamic properties inside the flow sheets. Okay, and those tools always use databases of parameters that allow us to characterize Cp of water, Cp of carbon dioxide, Cp of nitrogen. Okay? So, now that I have a way to characterize flows, I can combine the mass and energy balance and the characterization, which means that I will be able then to characterize apply the first principle of thermodynamics. Typically, but we have to be sure, is that there will be no big dynamic or batch storage effect, so no accumulations, which allows me to write equations that are in stationary or steady state, which means without accumulation. This is typical for a lot of industrial processes, not in the pharma because there are a lot of batch, but in most of the industrial processes, they try to operate in continuous mode, which means that there is no accumulation. And then I will be able to write the mass balance of the system and the energy balance of the system. And I will even be able to characterize the exergy balance of the system by calculating the difference between the exergy that is entering in any of the subsystems that I'm considering and the exergy that is leaving the system. The difference between being the exergy that is lost in the system. And everything is calculated with the help of the constitutive equations. I think that, yeah, just some remark on the approach. Characterizing flows means that you are going to calculate enthalpies, you are going to calculate and for this you will need temperature and pressures, and all those values came from sensors. Okay, and all those values also came from the description that you are doing from the process. So, for example, it might happen that you will write a very nice energy balance by making one assumption: there is no leakage, and in reality there is one. Okay? Might happen that it is hidden and you will not see it. Okay, so it means that you will have to be careful and be sure that you are not losing information, okay, by writing the configuration. Another dimension that is important is that this analysis allows you to see under which state and thermodynamic conditions all the flows that are entering and leaving the system are. And this is especially important for the streams that are leaving the system. Okay? So if you release hot gases at 400 degrees C, you will characterize them in form of energy and in form of exergy, and you will quantify the amount of energy that you release to heat the birds or to heat the fishes, right? And this is important to identify because this is going to be defining the opportunities for energy savings. Okay, when you draw the energy balance, you do not have to forget about the enthalpy of formation. So if you have chemical reactions, and combustion is a chemical reaction, adsorption is a chemical reaction, you have to account for the energy of the reaction. Otherwise, you will lose information. Okay? And when there are measurements that appears to not be consistent, we have always the nice idea of saying, oh, there is a difference, therefore there is a loss. Okay? When an energy balance is not closing, okay, it's possible that there is a heat loss. Okay, I'm not saying that heat losses do not exist, but at least the heat losses can be characterized. And so it means that the differences are not necessarily coming from a heat loss. It can be an error of sensor or something that you have forgotten. So don't forget to add the reasoning into the measurements that you are doing so that you can transform. So I'm writing here. So there is a difference between the losses and the ignorance. Okay? Everything is not losses, right? And then afterwards, you will be able to characterize the energy efficiency. So, for example, how much energy you spend per unit of product, how much you pay per unit of product, how much you pay per unit of value of the product, and how much exergy you spend per exergy in the product, for example. Okay, so what you can see here is that there is a list of key performance indicators. It's not only one. Okay, and here I'm adding also something which is sometimes difficult to accept. Okay, is the fact that I'm going to sum lower heating value of a fuel with the electricity that I'm producing. Okay, and we have the intuition that as I can burn the fuel to produce electricity, that I will have less electricity than the amount of energy in the fuel. It's not so easy to make the sum, okay? A priori exergy is a little bit more rational, I would say. Okay? But even there, it's not so easy to write. So the electricity is always a problem. Electricity is always a problem, and one way of going back is to transform the electricity back to fuels. But in this case, I need to know what was the energy resources that is used by the electricity supplier to produce the electricity that I'm consuming, so that I can then go backwards and identify the amount of fuel that is needed to produce the electricity that I'm consuming. Okay? The problem is that we are on the market, and therefore I have to find what we name the electricity mix. And here I'm just showing you different options, and you can see that due to the consumption, the efficiency of the conversion, and the content of the carbon dioxide emissions per unit of kilowatt hour, you can have very, very different results when you are valuing the electricity. And then you have even to, and this is important when you are exporting electricity or when you are reducing the electricity consumption. If you are exporting the electricity consumption, you will have even to make the assumption about what is the status of the market of the electricity, because if I'm putting more electricity in the grid, what is going to happen? Is that the coal power plants will be operated at a lower rate, or is it the fact that I will have to invest less production with natural gas or with PV panels? Okay, and this would, of course, lead to very different results. Another difficulty is the allocation. The allocation that is needed when you have more than one product that is produced. Okay, so I'm consuming electricity and heat to produce two different types of polymers. Okay, but perhaps that one is exothermic and the other require less, is endothermic, or another product that is endothermic. And you will see that it will be quite difficult to allocate a saving to, or even a consumption to a given product, because as soon as you change one, the other is going to be affected. Okay, so it's not always so easy to do the allocation, and here I'm proposing different types of allocation to allocate the energy consumptions to the right product. So you can allocate by mass, so it means that then you consider that the mass are equivalent to the market value or to the energy or to the exergy value. So in this case, what you take as an importance in the product is measured either by a cost on the market or a thermodynamic value of the products that are produced. Okay, so it means that it's not always easy to do this allocation when you have more than one product. And I will conclude by the fact that it is important to make afterwards consistency check at the system level. So it means that you will look at what is the amount of energy that is entering and what is the amount that is finally entering in the process, and what is then afterwards leaving the process in form of cooling, in form of export of heat, or in form of recycling here. So these kind of diagrams are quite interesting, because normally we have to be able to explain all the flows that are in this diagram. Okay, because the energy balance is closed. Okay, so it means that if we identify this kind of unexplained here, okay, it means that perhaps something is missing in our analysis. There is perhaps a leakage somewhere, it's possible, or I have forgotten something. Okay, and of course, as all those values are coming from measurements, they are prone to errors as well. It means that I will not end up with, I will not stop at 100% explanation, but let's say the 1% here, which is, or the 3% here that is unexplained, is most probably acceptable and hidden in the errors in sensors. Okay? Right, so I'm going to stop now. Do you have questions? Okay, then we are going to make a break, and then Francesca is going to explain. So sorry, we have a full afternoon, so it means that you will have to work a lot. So Francesca is going to explain you the first exercise, which in fact consists in identifying from an energy bill what is the energy that is delivered to a product. Okay, so you will have a flow sheet to analyze and to characterize in such a way that you will be able to calculate what is the cost of energy, of heat that is delivered to a product. Okay, so we start again in 15 minutes.